Okay, good afternoon. Let's start. So before I start with the lecture, any questions on the homework or the design assignment?
Can you go over the last question on the homework and kind of explain that to them?
Sure. Okay. Anything else? That's the only one? Okay. So let's do that. So what the last question on the homework, those of you on the call, basically says the following, that I have a system which has an input, 8-bit input called X. It has 8-bit input, 8-bit output called Y. So essentially, you're designing a box. I'm getting an 8-bit input X. I'm producing a Y, which is 8-bit output. And what this box does is, it at any given time, y of n, where n is the time index, so I'm going to explain that to you very briefly, is 0.25 times x of n plus 0.5 x of n minus 1 plus 0.25 x of n minus 2. So think of it this way, that on x, I'm getting a series of numbers. It could be a sensor, let's say a temperature sensor, and let's say every second it is giving me a new reading, and readings are 8 bits in value. So if I were to be observing on x, I will be getting first reading x of 0, next reading x of 1, third reading x of 3. Each one of these are 8-bit numbers, and specifically in our case, these are 8-bit 2's complement numbers, so they could be plus or minus. So I'm getting some number, some 8-bit number, some 8-bit number like this. And what we are doing is we are taking at every time I take the current sample and I take the previous 2 sample and I do this weighted average of them. So this is very commonly used to smooth out signals. So like when you read data from sensors and all, they tend to be noisy, and you want to kind of smooth them out.
Because it's 2 complement numbers, does that mean that if I were to do shifting, I'd have to like re-implement another like 1 bits in the front or something like that?
Okay, so division, as you recall, divide by 2 is a shift right by 1 position. The difference between so if you had ordinary positive binary numbers, so you were using your n bits only to implement positive numbers, then you would shift in a 0. The difference with 2's complement is that you are going to shift in the sign. Okay, so you can check that out, but that's that code that you want. Okay, so let's take 4-bit numbers. So 4-bit 2's complement numbers go from minus 8 to plus 7 if you had 4 bits. Okay, so they go from 1 0 0 0 to 0 1 1 1. Now let's say I divide 7 by 2, so then it becomes 0 1 1 1, shift right, it becomes 0 0 1 1, and then there's a remainder. And if on the other hand I take minus 8 and divide it by 2, I expect minus 4, so it will become, so what we have currently is 1 0 0 0, it will become 1 1 0 0, so I'm going to be shifting in the sign value. And 1 1 0 0 you can check from our lecture notes, would correspond to minus 4. So that's how the shifting works. Now, one thing which some of you asked, what happens to remainders and stuff like that? So when I divide by 2, there's a possibility of a remainder, obviously, right? And 0.25 is nothing but divide by 4. So shifting by twice, shifting 2 times. But your input is n bit, your output is n bit, but inside the box you can have more bits. So the example I was giving was, let's imagine x0, x1, x. Get screwed up out here. This should be x2, x0, x1, x2, or let's say 1 to 1. Okay. So if I had any number of bits, arbitrary number of bits, then 1 to 1 weighted in that fashion should result in 0.25 plus 0.5 plus 0.25, which should result in 1. But if individually I were to divide each one of them, so if I take 1 and divide it by 4, multiply by 0.25, 5, and I know the remainder, I get a 0. Same thing for the next one, same thing for the next one. So if you were to do it kind of naively, your answer would turn out to be 0 if my samples were 1 to 1. But if you were to retain those extra bits and then do the truncation only at the end, then you will get the correct answer, which is 1. So that part is going to be important, and you will be penalized if you sort of truncate all through. That is, your answer would have more error than otherwise. So that's one thing. The second thing is what happens when I am at the end when you are going to divide by this thing. At most, there should be a 1-bit error, right? I mean, whereas if you were to incur a 1-bit, ignore a 1-bit remainder in each one of the individual variables, the first term, the second term, and the third term, your answer would have less accuracy. So create more bits inside the box and then truncate at the end. So that's the message. Yeah.
Since the homework for this problem asks for like addition logic, does that mean we use multi-bit adders now?
Say it again.
Can we use multi-bit adders for this?
Actually, just read what it says. Can you read it for me?
You can use standard combinational stuff, which includes simple gates, mux, demux, encoder, decoder, arithmetic functions, etc., except multipliers.
Yeah. So,
Yeah.
Okay. So you can use n-bit adder. Okay. I mean, pretty much. I mean, yeah, the kind of adder that we had. So this is an n-bit adder of the form where you have full adders and scale up with it.
Could you write down the detailed implementation for the insight, like how to?
No, I won't. I want you to do it.
No, I mean the how to make it more basic in insight.
Oh, okay. So I'll give you an example how you can do it, right? I mean, so let's say x of n was let's take an example. Let's say x of n was 1, and let's say n was equal to 4, right? So I have 0, 0, 1 as the value, and I want to divide it by 2, right? If I were to shift it by 1, I'm going to get 0, 0, 0, 0. But that doesn't help me, right? So what you do is you introduce an additional bit after an implied decimal point, and now this is the value you are going to have. And since in this case we are dividing by up to 4, so I will actually maintain 2 bits out here. Okay, so this is how I would do. So I'm going to extend my n bit by 2 additional bits, which are for after the decimal point. And I'm going to do so I'm going to take my numbers and assume that whatever number is coming in, dot 0, 0. And now I'm going to do my divisions, do all the addition, and then ignore the stuff after this. Okay, so this is fixed point stuff. Or another way of thinking it is, imagine as if I had multiplied all the number by 4. Right? If I multiply the whole equation by 4, then my equation looks like x of n plus 2 times x of n minus 1 plus x of n minus 2. And I do all of that, and I can divide it by 4, right? I mean, and now in that case, if I'm multiplying everything by 4, that means I've introduced 2 additional bits. So that's another way of thinking. Okay, so again, I guess the more main thing I wanted you guys to kind of think about is that temporarily I can jack up the number of bits, but output is still back to n bits. Any other questions on this one? There was one question that someone asked in my office hour, which is a good one, and it's the following. So let's say now you have computed the final answer, final thing, and now you are dividing. Now you are kind of let's ignore this problem for the moment. Let's say I give you a number 5, and I say divide it by 2, and you have to retain the same number of bits. So 5 is 0, 1, 0, 1. And you divide by 2, so you shift right, you get 0, 0, 1, 0, so you get 2. So what's happening is that I am truncating it downwards. I'm truncating it towards 0. The question is that let's say I give you a number like minus 5. and I divide it by 2. Should the answer be -2 or should the answer be -3? Which way should I, right? I mean, should I truncate it towards -infinity or should I truncate it towards 0? And computers use both policies depending upon their implementation, so there is no one correct. Firstly, there's nothing wrong or right about any one of these. It depends upon what hardware you're using. In this problem, you'll probably face the same situation at the end when you are taking care of it. You can do either one. So for negative numbers, you can either, if you have a remainder, you can either say that I'm going to do it towards 0 or I'm going to do it towards infinity. So again, a number like -5 divided by 2, is the quotient -2 or is the quotient -3? The answer is, it depends on what policy you use. For positive numbers, we never even think about it, right? If I give you a number like 5, you will always say remainder is positive, right? And so 5 divided by 2, the quotient is going to be 2. For negative numbers, the answer is less clear, and you will find both kinds of implementations. Any other questions? Okay, so we'll move to the regular lecture then. Okay, so we had looked at counters, we had looked at timers. So the next module that we had started looking at was shift register, or shifter as it's often called. And the basic idea out here is that bits enter from one side and they are discarded from another side. And someone pointed out to me at the end of the lecture that the example I was doing, I was showing shifting to the right, even though out here it says shifted to the left. Okay, so actually, if we were to ignore this thing for a moment and I were to look at what the text actually says, in the text what is happening is I have a bunch of D flip-flops, and every clock cycle I shift in a 0 here, I shift in SN here, and then content of the first flip-flop move to the next one. In parallel, all of them are moving, so they're all transferring to the neighbor, and then the final one is discarded. Okay, so in effect, so if SIN was 0, then the effect would be multiplied by 2. But SIN could also be 1. And the shift registers, as I mentioned last time, they're used to take kind of serial data which is coming in and then collect them into a word which you can then read out in parallel. And many communication interfaces use that. So let's see how something like this would be implemented. So first thing is, again, remember, our strategy with Datapath is that we try to write the next state and the output logic as equations, kind of like in a programming language. So output in this case is the n flip-flops. So the output is just equal to the state, n bits of state. And the next state function is the following. It says that if reset is high, then next state is 0. So next state is an n-bit thing. So it's saying all the n bits of my state register are going to be made to be 0. Otherwise, next state is, and there is this notion, it says next state. So remember, next state is n-bit. Okay, so I have to, so this is a notation which is used. It's basically saying upper n minus bits of next state are the same as the current state, the lower n minus 1 bits of that. Okay, so I go from n minus 2 down to 0. And then the lowest bit of next state is going to be SIN. So this particular notation that we are seeing is kind of basically saying take the lower n minus 1 bits of state of the current contents of the state register and then append to it, or at the 0th, at the least significant bit position, append to it whatever the value is on SIN, and that new n-bit entity is what I'm going to feed into next state. So that's the effect of that shifting and while making SIN coming in that's happening. It's really a sort of a wiring operation, as we have often seen. So this is what is happening out here. I have a mux in front of a n-bit state register. So I have a state register, I have a mux, and the way I have wired up is the following. So this is an n-bit mux. I can either feed all zeros to this thing, so that's a reset case. Whenever reset is high, all zeros go in. Otherwise, what's happening is, if you kind of look at this thing carefully, what's happening is SIN goes to the 0th wire, and then the lower n minus 1 bits of whatever was the current value of state, so which is feeding back out here, the lower n minus 1 bits are feeding into the upper n minus 1 bits here. And this bit, n minus 1th bit, the topmost bit out here, it's not being used at all. So it's just a wiring operation, and every clock tick, what will happen is that SIN, the current value, the value of SIN at that clock tick, feeds into the lowest bit. So SIN is kind of feeding in out here, as you can see. And so if I were to be observing the output, what will happen is, on the output, it would be shifting left, and the SIN will keep appearing on the LSB every time. And if I'm trying to collect n bits, so I'll do n clock. So let's say someone was sending me n bits of data serially. So what I'll do is I'll let the clock tick n times, and after the clock has ticked, the n bits would have collected in the state register, and I'll read them off. And I'll do that again for another n cycles and keep doing it. So I can kind of collect bunches of inputs.
Can you explain why that is so?
Oh, that's the definition. So so why? So remember, look at the specific. It said if reset to this, otherwise this. Whenever you see this kind of statement, if condition, the next state is some value, otherwise is some other value, it should remind you of multiplier. Okay, so that's the heart of being a multiplier, right? Based upon a control, you are connecting either one input or another input to the state. Any other questions on this one? So you have seen this rewiring of as a shifting operation many times. You saw it in homework, you saw it in midterm. This shift register kind of combines it with a state register to create something which now takes data coming in sequentially, bit by bit, on the input line, and making it available as a bunch of bits in parallel out here. Now let's create a more sophisticated shift register. So the shift register we just did shifted only one way. It shifted left. But oftentimes we may need to kind of do both ways. So in computers, CPUs have registers where variables are stored. And then a common operation that many CPUs provide, if any of you have done CS33, for example, you would have seen in assembly language that actually anyone has done CS33 yet? Okay, very small number. So that's a class where you learn about the structure. That's the first class where you learn about structure of the computer. So CPUs have registers where variables are stored. So when you write int x in your program, that x eventually at some stage is going to sit in some register, a memory, usually 32-bit or 64-bit. And then the computer provides you, the CPU provides you with operations like shift left or shift right. And so the hardware inside the CPU has to be capable of taking a register and kind of shifting it either way. So oftentimes it is done using this kind of capability by providing mechanisms so that contents of a register can be moved each way. So that's what we seek to do. So this register has a reset input as before, which will make the content 0. But now it has a left control. Whenever left is high, out is shifted left with input SIN filling in the MSB. If, on the other hand, right is asserted, then the out is shifted right with input SIN filling in from the MSB side. And then finally, there is something called load, in which case I take a parallel word and load it into the register. Okay, so I can load data serially from left, from right, or I can load all the n bits into my register in one go. And otherwise, out is unchanged. So I have all these operations. I can reset to 0, I can shift left, I can shift right, I can do a load, and I can leave it unchanged. So clock tick coming in, nothing happens. So faced with something like this, again, you first think in terms of how to express it in kind of this programming language type formalism. So our output, again, in this case, is again the same as the content of the state register. And now we have to think about how the state is changing. So if reset, next state is 0. That follows from the definition. If not reset and left is high, then next state is equal to state n minus 2 colon 0 sin. This is what we previously saw. So what's happening is next state is an n-bit entity, and we are basically saying upper n minus 1 bits of that are the same as lower n minus 1 bits of the state register, and sin becomes the LSB. If, on the other hand, reset is 0 and left is 0 but right is high, then I go the other way. Next state is equal to sin in the MSB, and the lower n minus 1 bits are equal to the upper n minus 1 bits of the state register. So I'm shifting right. Another case is if reset is 0 and left is 0 and right is 0 but load is high, then next state is equal to in. So I have a parallel input signal also. So my box looks like the following. It has an out, it has a in, these are n bits, it has a serial in, which is 1 bit, and then it has reset, left, right, and load. It has a bunch of control signals. So it has 4 control signals, it has a single bit serial input, it has an n bit parallel input, and it has an n bit output. So the logic is listed out here. So it follows from the specification. So again, I don't know, your very first thing is faced with something like this, first think about like what the description is. So what we have in plain English out here is kind of listed in a more formal way so that it's less ambiguous. And output again in this case happens to be just the state. And then once you have that, looking at this, you should remind you of multiplexers again. I have a bunch of ifs, so I kind of write it like that. So this time around, we use a 5-to-1 multiplexer. So that 5-to-1 multiplexer is taking 1 hot control input. So there's a 5-bit of controls out here. And I have all the 5 cases listed out here. This case, where I'm feeding the 0, corresponds to reset. This one, where I am just taking the current value and feeding it back, is the otherwise case. The one where I'm taking the in and feeding it, this is a load case. Then I have this SHR, which is taking the current state as well as SIN, and this is just going to be wiring. So this is just wiring. These 2 boxes are just rewiring up. So one is shifting right, the other is shifting left. So those are my 5 cases. And then I will have some logic. So this is some random logic out here, which is taking my signals, reset, left, right, and load, and is going to generate the right signals for the multiplexer. So for example, if reset is high, then the signals out here, the 0th wire should be high because that's what resets, and everything else should be 0. If reset is high, so if reset is low but left is high, then some other wire. This is going to be one coded out here. So this pattern that we are seeing again and again, which is we write it down in a set of conditionals. The conditionals tell me about a multiplexer, and then we have to design this combinational logic which captures under what condition which input of the multiplexer kind of flows out. So we've seen it now several times. We saw it with counter, previous shifter, shift register. This time around also same story. So almost anything. I mean, you can. A lot of these systems can just basically be thought in these terms. That you think of a next state function and you think of a output function written in terms of these arithmetic type expressions, and then just map them into hardware using muxes and some combination. So, and just to highlight the point, these two boxes, SHR and SHL, are just rewiring operation. They're taking n bits and Sn and kind of just rewiring them out into a new n.
Do you need to specify which n minus 1 bits? Because aren't they different for two?
Yeah, you need to specify that. So I guess from the context, yeah. So in one case it will be the upper n minus 1. Yeah, right on. So it's just saying there are n minus 1 bit. So the point he's making is I'm getting the n bits out here. So let me go back to the previous slide because probably seen around there. So when I'm shifting left, I have to take the upper n minus 1 bits. Take the lower n minus 1 bits. So in that case, these n minus 1 bits are going to be the one which are going to be n minus 2 colon 0. Whereas these, where I'm shifting right, they would be n minus 1 colon 1. So that's going to be the more accurate. Any other questions on this one?
Did you choose one hot mux because it has 5 bits? So basically,
Yeah, I mean, if I'm not using one hot, if I was using like a 3-bit binary encoded, then it would be an 8 to 1 multiplexer, which would be more costly. So these kind of multiplexer, 5 to 1, you could implement them using our tri-state buffers. If you recall, I can use 5 tri-state buffers, each one of them being controlled by a different one. I recall a couple of students did it back when the bit was
would you still do that with 7-bit mux?
Huh?
Would you still use one hot for a 7-bit mux?
Yeah, I mean, yeah, sure, there's nothing wrong with it. Yeah. Then again, look, one message I would like you to take it away is there is no right or wrong answer. Okay, it's just what is more efficient or less efficient. Okay? You can take the same functionality and implement it multiple different ways. And like beauty is often in the eye of the beholder. What your metric is can be different. Some people care about dollar cost, some about speed, some about power consumption. So again, it kind of depends on the context. But from my grading in the midterm, you would have noticed that I did deduct points when things were far more inefficient than they ought to be. And again, kind of to repeat a point which I sent it in my Piazza email, when you are adding one, when you are comparing against a constant, these kind of things, if you are, so let's take comparing against a constant. If you are not using a full-blown comparator, functionally there is nothing wrong with it, but it's so inefficient that I'm just forced to deduct it. So, just be careful for these kind of things. I mean, a comparator is meant to compare two unknown numbers. When you're comparing against a known number, you can do things more efficiently. Likewise, I mean, here muxes, I mean, if you cannot use a mux with numbers, the number of inputs being a power of 2, then something like this might work out. Okay, any other questions? Okay, so let's move on. So this question came up last time also. So now I have shown you two ways of designing sequential systems, right? One is you start out with this FSM. You think of your state machine, think of your system as states. You're moving from state to state. And then the other way I've kind of shown is that you think of your next state function as the pseudocode programming language kind of stuff. And one we call as finite state machine, the other we call Datapath. And in any given, I mean, most digital systems are far more complicated than what we have. And the problem as a designer that you face is, which one should I use where? And the answer is really, you need to use both. Most systems have some parts which are better expressed as a data path, and have other parts which are best expressed as a finite state machine. Generally speaking, finite state machine corresponds to things where things jump around, like iterations and if then else and those kind of things. Whereas data path tends to work better where things can be expressed using simple expressions. But the boundary is never clear cut, and given a problem, you can certainly always do it entirely one way or entirely the other way. Again, it's going to be how easy or hard it is. I can take a 32-bit counter and certainly write down all the 4 billion states and do the Carnot map and whatnot, and we'll probably end up with the result after a few centuries. Not very helpful. So you have to kind of use the best abstraction for the job. And that comes with experience. I mean, with lectures alone, I can only point to you obvious cases, but many a times you're going to face these decisions and sometimes go by your gut feeling. I mean, if it smacks of being like arithmetic or operations being done in parallel in bits, then it's a data path. If on the other hand, it's a lot of decision making going on, if this, then do that, that kind of stuff, which is often takes place in programs, like if it's a protocol of some nature, those kind of things, they probably suggest that it should be FSM, done as an FSM. But so again, kind of, they are, deep down, they are exactly the same. You take one, convert to the other. It's really what works easier for a particular problem at hand. So this, so real systems often have both components, and what ends up happening is that in real systems, you then would have part of the system implemented as a part which is where you started out as a state machine description and mapped it into hardware, and another part which would consist of something where you started out as that pseudo program code and mapped it into multiplexers and adders and stuff like that. So, and what would happen is these two parts would talk to each other. So what you really end up with now is a kind of an interesting kind of system where there are actually two sequential systems which are talking to each other by exchanging some one system's output is another system's input and vice versa. And of course, when I take together two sequential systems and wire them together, the bigger system is still a sequential system. And that email I sent around on Piazza saying that for some pattern detectors, it might be good to think of your pattern detector as two pattern detectors which are working together, and then you combine their output. That's an example where I have two state machines, and I was taking their output, combining them together, and using them as output. Okay, so sometimes, in many cases, it's better to think of a system as not a single program or a single state machine, but as multiple things doing things concurrently, because then you can focus on one or the other. Other examples, let's say you're designing logic for a telephone answering machine. That telephone answering machine has to do many things in parallel. It has to always be on the lookout for someone lifting the handset. It has to be on the lookout for the telephone company sending the signal for an incoming call. It has to be on the lookout for the user pressing, let's say, a play key. All of these things it has to do simultaneously. So let's say you were writing a software program and you had these three inputs which you have to do simultaneously. What strategy would you use? Yeah, so imagine I have whatever 3 inputs to your system. You have to monitor and do something when something happens when a call comes in, something happens when a button is pressed, something happens when the handset is lifted. So how do you approach writing a software program where you could do all these 3 things? Okay, let's simplify things further. Let's say you are tasked to observe 3 doors which you cannot simultaneously see and report whenever someone enters through them. So you cannot simultaneously see them. So what would you do?
For the last question, should we start with, probably I will start with this stateless chain model and try to simplify the state table.
And then I'm not talking about digital logic. I'm just talking about you're writing a piece of software.
That's what we're trying to do. Just to figure out which state.
And I don't think this is taken on. I'm asking something simpler. You're writing a piece of software there are three things that you have to monitor for. Of course, there is no command in Java or C which says monitor those three things. So what do we do?
We just like loop through and just check each one, and then if
Okay.
one is like satisfied, you just go to it.
Okay, good. So that's excellent. So that's one way of doing it. I can write a single program. I have a loop. In the loop, I say, is the handset lifted? If yes, do something. If not, is the whatever play button pressed? Do something. If not, did the telephone company send me an incoming call signal? If yes, act upon it. Right. So this is called polling. I check one, I check the other, and keep doing it. Okay, so that's one step. Is there a way when you write programs you can do all these three things in parallel? How many of you have heard of threads? Anyone? Threads? No? I see a hand raised out there. Sometimes they say, what do threads do? Go ahead. So, what is a thread?
I kind of referenced this third grade. You can just run multiple threads, and then it's like they're all in parallel.
They're all parallel, right? So you can, within a program, you can have multiple threads. They can do things in parallel. They share, the operating system kind of makes sure that they kind of run together. Maybe your computer may even have multiple CPUs. So threads are something that most programming languages provide as a way to do multiple things in parallel. Essentially, instead of writing a single program, you write n programs. One for one for another, one for another, and then you have them talk to each other. So that way I can observe one input, another input, another input. Same thing kind of out here, that oftentimes when you're designing a sequential system, instead of designing a single sequential system in one go, you design subsystems. One for doing one thing, another for doing something else, another for doing something else, and wire them together. So in the pattern matching example, if my task is to be on the lookout for pattern 1 and pattern 2 and pattern 3, I can either design a single state machine which does all three of them, or I can design one for one, another for second one, another for third one, and then OR them together. Or I can do other sort of interesting combinations. This data path control takes the same idea of doing multiple things simultaneously towards this notion that in complex systems, there are things which are data path type things, and there are things which are control oriented things. So what we'll do is, given the specification of our system, we are going to chop it up into two halves. One where we say, this part is best described as a state machine, and another part where we say it's best described as a data path. That partitioning is really kind of a design skill. And once you have done that, you kind of implement the two and have them work together. So a very general, this is a very common strategy, and the way the system ends up looking is that one part of the system is implemented through a state machine, and that will be getting some inputs from the outside world. We are going to call them the control inputs. It is also going to be sending some outputs to the outside world. We are going to call them the control output. Then I'll have a data path. Inside the data path, we'll have our usual culprits, mux, adders, those kind of things. They will be getting inputs from the outside world. We are going to call them data inputs. It will be producing outputs for the outside world. We are going to call them data outputs. But more interestingly, the two will talk to each other. Control state machine, it will send some of its outputs are going to go to the data path, and those we will call as command. So the controller is telling the data path what to do, and the data path, some of its outputs will go to the controller, and they are called status. The data path is reporting something about the status.
So does that mean that the main difference between an FSM and a data path is that a data path has hubs for sure, or something related to that?
So you will design a state machine by starting from, or you're designing the controller by starting with a state machine and going through one-hot coding and those kind of things. Your data path you will design by starting with those expressions and getting it there. And as we saw, usually we end up using muxes and stuff like that there. And the reason is because data path consists of expressions which are dealing with n-bit variables, right? So we were doing like a counter timer example and all. Whereas state machine was dealing with this unstructured graph with transitions happening between them. So, for example, if you were to, let's say, let's imagine I'm getting a stream of numbers from a sensor. They are n-bit numbers, and then depending upon, and there is a user, those numbers are coming into the box I have designed. On that box, there is also a user control, perhaps a few switches. And the user sets those switches, and based upon that, the box does something to those sensor data. Like, for example, maybe it smooths them out, maybe it looks for edges, maybe it multiplies it by some factor. Okay, there are different operations my box can do on the sensor data. Which operation it does depends upon what the user sets the switches to be. So it's kind of a simple programmable sensor handler. So in this case, based upon my switch setting and all, what is happening, that's kind of the control part. I'm controlling it. The actual operation on the sensor data, whether it's doing a multiply or whether it's doing a smoothing or whatever, that sounds like data part. It's stuff happening on the sensor data. So what is data, what is control? I mean, oftentimes this kind of is dictated by sort of, tends to be very obvious at some level, which is arithmetic and stuff like that tend to be data, kind of logic, and then if then else, those kind of things tend to kind of go into control. When you're writing a program, variables which you are using to do things like x is equal to y plus z, sine of z, those kind of things, they are arithmetic, they are data. On the other hand, variables like for I equal to 1 to 10 do something, or like if I less than 0 then do something, those things are control statements. Okay, you are kind of based upon those, you are kind of going one way or the other. So that's the job of a controller. So that's the separation. Sometimes it's very clear, sometimes it is not. But any general system can be viewed as having this control part, which is this state machine based design strategy, and this Datapath part, which is designed using what we saw earlier in this module, which is pseudocode and which we map it to. When you look at the implementation, Datapath will tend to have things like n-bit adders, n-bit multiplexers, and all, whereas controller would have some unstructured logic. So this overall stuff, this is my entire sequential system. This entire stuff. Okay, so it has control inputs, data inputs. Those are the inputs. It has control output, data output. Those are the outputs. Internally, we made it as a controller and a data path, and those two talk to each other using some signals they are exchanging. And so once you are faced with more complicated design, this is the strategy you will have to take in general. And in fact, the design assignment that you have handed out, if you notice, there is a optional part with a very significant extra credit component where you have to reprogram, you have to change the code which is used to unlock the lock. That part really kind of corresponds to this data versus controller kind of thing. You can do the first part entirely as a controller. The second part, you would probably have to do it as a very simple data path in a controller. So as the complexity of systems increase, you are forced to kind of go towards these kind of designs. So data path computes the next state using multiplexers and other such units like adders. Also, they correspond to variables in the program over which you tend to do arithmetic, whereas the controller computes this next state using a state table kind of thing. So this we designed using the approach we did it in the previous module. And then you kind of wire them together. So control FSM sends commands to the data path. It tells the data path what operation to do, and the data path sends back status to the controller indicating exceptional conditions like, I added an overflow happened, or that x is greater than 0, those kind of things. So we'll see how it kind of works out with an example very shortly, but that's how the two communicate. And then inputs and outputs of the system are also divided into these things. So like in my example, the sensor data which was coming in, perhaps a 32-bit sensor data, and then the processed sensor data which was going out, these were examples of data type inputs. On the other hand, the switches that the operator was setting, or maybe LED light bulbs that were blinking with error condition and all, those would be examples of control type inputs. So again, it's almost like I said, when you look at a problem, you would say, yeah, this thing sounds like data, this thing sounds like control. There is no rule I can tell you, okay, follow this, this is a recipe. So let's look at a vending machine control. And then
So the command corresponds to the control state, and the state status to the data state.
Say again, the command corresponds to command is computed from by the output logic of the controller. So it doesn't have to be the control state. It could be something computed using the control state and the input state.
So same thing for the status.
Usually status from Datapath is things like adder overflow or output of a comparator, those 1-bit kind of conditions. Right? So like in your program, you often do things like if I less than 0, do something, or if I is negative, do something, those kind of things. So they usually correspond to the status. Okay? Command are things like do an addition or compare the two numbers. Those are the kind of things the controller would say.
Arithmetic results are the data state.
Arithmetic results are arithmetic results go into registers, which are the data states. Okay, let's look at an example now. So vending machine controller. So what we need to do is, we all use vending machines. So this is a machine which receives coins. So there's a coin receptacle where the user can deposit coins, nickels, dimes, and quarters, and it keeps collecting them, and internally then it computes what is the total amount of money you have deposited. And then at some stage, the user presses a button, a dispense button, to release a drink. And this machine is only one type of drink, so it dispenses it only if enough coins have been deposited. So drink maybe, let's say 75 cents. If you have deposited 75 cents, it will release a drink, otherwise not. And then if you had deposited excess change, then it will return a change, a nickel at a time. So it has a big reservoir of nickel. So if you deposited, let's say it was 80 cents cost, you deposited 4 quarters, it will return back to you 4 nickels. Okay, so that's basically what the state machine does. Now, as you can see, looking at this, there are control type stuff in it, right? I mean, button that I'm pressing, that's usually a control signal. On the other hand, clearly I also have to do arithmetic. I'm adding this, creating this sum. I'm comparing is the sum of money deposited enough, right? That's an arithmetic operation. So you could see just from this description that there are kind of both things happening out here. There's some control type stuff, then this stuff, return change. So what's probably happening is that there is a signal going out to some sort of a mechanism which releases a coin. So that again sounds like a control. I'm sort of sending a control signal out there. So from the specification itself, one of the things you should try to do is to sort of let it sink in and see, what part likely correspond to data operations and what part likely correspond to control operations. Again, sort of comes with experience, but you could there are usually some sort of things that you could look for. Arithmetic stuff implies data path. Single bit things happening imply control. So we have to partition this thing into data path and into control. So what we'll do is the data path will keep track of amount that the user has deposited, and the control part will keep track of the sequence. The user has to deposit the coin. If there is enough money deposited, then I have to serve. So I have to tell the drink mechanism to release a can, and then I have to dish out the change. So I have to let the money mechanism to kind of release four nickels in my example of 80 cents versus $1. So you kind of mentally so at the highest level, you kind of decide that, okay, this is a partitioning we'll do. And in this simple example, it kind of seems obvious that's the case, and sometimes there might be some ambiguity, is this control, is this data, where should I reside it? It could occur for things like, if I have an operation like, for I equal to 1 through 4, do something. Is I a data variable? Is I a control variable? Less clear. If on the other hand, if I were to say, for I equal to 1 through 4 billion, do something. It's very obvious that I'll implement I as a data variable. So same type of description can sometimes be very obviously data, sometimes very obviously be control, sometimes ambiguous. So looking at this example now, state diagram for control. So what we have to do is we are keeping track of money being deposited, accumulate the sum, and then when the dispense button is pressed, serve a drink, and when return change, 1 nickel at a time. So there are 3 main phases happening. Letting the user deposit the coin, waiting for the dispense button to be pressed, and then taking action accordingly. So when we start out, after a reset, we are in this mode called deposit mode. And in the deposit mode, the user can keep depositing the coins, and we'll kind of stay put there. In the deposit mode, then what we do is, if the user presses the dispense button and there are enough coins, then I'm going to go into a serve mode, or enough money, then I'm going to go into the serve mode. In the serve mode, I'm going to serve the drink, and then I'm going to go into a serve to mode. And in the serve to mode, there are 2 possibilities. I'm going to check whether I owe any money to the user or I don't. So the other thing which is happening is, you see this done signal. So the idea is that I'm waiting for the mechanism which is releasing the can to tell me that it has dispensed, that it has successfully released the can. So I go into serve on mode, wait for the can to be dispensed. So that's the done part. Then I come out here, and then I say, okay, if I'm done and there's no money left, I go back to deposit mode. If on the other hand there is money remaining that which I owe to the user, then I go into this mode where I have to dispense the change. So I again do the same thing. I keep releasing more and more change until all the money has been removed. I don't own any more money to the user. And once that is done, I will go back to the original deposit scale.
Does that mean that the thing that releases the can and you wait till it's done, can that be considered a data path too then? Because it's a sensor based?
Yeah, I mean, you could think of it as a mechanical data path which is acting upon some commands I'm sending to it. You could. I mean, those things are in a way a mechanical state machine, some mechanical data path of some kind, or mechanical sequential system. That would be what it will become clear, but the signal coming from other parts of the system. Okay.
What's the use of server to and change to?
It's basically iterating, right? I mean, because I have to. So the serve to is waiting for the point for the can to actually have been successfully released. Okay, so I request the mechanical mechanism to release the can, and then I have to wait that it actually did it. Just wait until.
What's the meaning of done prime and zero?
Done prime means that done has written back to zero.
Why is it prime?
or it's negation. Prime means
Nothing.
I think we'll see how it is. It's probably that the sense is reversed. Okay, so the other thing which is happening out here is that for clarity purposes, self transitions are omitted. Okay, so basically, like for example, out here, there is a self loop well done, which has been omitted out here. Okay, and likewise in many other places. So there is also a self loop done here, which is omitted. And likewise, there is a self loop out here, which corresponds to not dispense and enough, and so on and so forth. So that's one important point. Self loops have been omitted. So an FSM stays in a state if none of the outgoing conditions are true. Okay, so data path. So now again, so the strategy is you have to kind of start developing kind of a high level sketch of what the two sides are going to look like, and then kind of gradually refine them. So in the data path, so we have a data path, and that data path is going to talk to the control machine. Okay, the controller. The controller is receiving. So this control FSM is what we designed, what we laid out in the previous slide. This controller is going to get the reset signal. It is also going to get the signal saying whether a nickel, dime, quarter has been deposited. So every time a coin is deposited, there's some sort of signal. There is a dispense, there is a done, and it is sending out signal called serve and change to the can mechanism and to the change return mechanism. This top part is my data path, and in this data path, I have to do some operations. Every time a coin is deposited, I have to keep track of how much money the user has deposited, and every time a coin is deposited, I have to update that. So what you see out here is that there's a multiplexer. It has values 1, 2, and 5 out here, and you see this plus and minus so that I can do an adder or subtraction. I have a register out here, which is I'm going to maintain how much money I have that the user has deposited or I owe to the user. I can reset it to 0, which is through this path. I can hold its value. I can increment, add or subtract to it some other value. I can also subtract the price from it. So intuitively, if you think about it, my data path has to be able to do the following operation. Every time there's a coin deposited, I have to update the money I have. So if a quarter is deposited, then I have to add 25, or nickel, 5, and so on and so forth. Whenever, then another operation I have to do is to compare against the price. So when the dispense button is pressed, I have to compare whether the price is more or less, whether the money I have is more than the price or not. Only then I will release the can. And then finally, when I'm returning the money, as I'm returning the nickels, I have to deduct 5 every time I return a nickel until I go back to 0. So intuitively, that's a set of operations you expect the data path to do. And this particular data path, where I have basically I have a register to store how much money I have. I can hold the value. I can reset the value. I can add or subtract nickel, dime, quarters, and price to it. And then finally, I have to do something whether I have enough money or not. So there's a comparator, as well as I need to compare against 0. I have that comparator also, and I feed that to the control FSM. So there's stuff going from the data path. The multiplexers are controlled by the controller. So what's happening is controller is going to tell the data path what to do, whether to compare, whether to do what not, and it is basing that information on the controller is going to base its action in part upon what it's seeing from the outside world, coin being deposited or stuff like that, as well as what it is receiving from the data path. And then there is this done stuff which is coming from the mechanisms, and then this serve a can or serve change, which I'm telling the mechanical part of the vending machine to do. So again, at this stage, we don't have everything fleshed out, but at least we have given our data path enough assets to kind of do the kind of things we wanted to do.
Does that mean usually like the control FSM, like the part it interacts is usually like the max control piece?
Very commonly. So the signals from the controller usually go on to control multiplexers, as well as things like adders, subtractors, and all, okay, those kind of things. And the stuff that comes back to the controllers is typically the output of things like comparators or the overflow bit of an adder, those kind of things. That's a common pattern that you see. There are some exceptions, but that's commonly. So the question that he's asking is like, if you see out here, the lines going out of the controller, they're all going to the control input of the mouse. And the question was, is that always the case? It's very, very commonly the case. And likewise, if you see the bits coming back to the controller, these things, these two bits which are coming back, these are the outputs of the comparators. So these are 1-bit stuff which is coming back, which is telling something about the status in the data path. They're telling it back to the controller. So this design pattern is very common.
Did you try the previous slide? I was just wondering, or the slide with the state diagram, I was wondering like, which part of this would you say is the control and which part is the data path?
This is all control. There is no data path on this one. So this is essentially what we expect that control FSM to be doing at a high level, these different phases of operations. So again, controller is designed using state machine. Data path is designed using the kind of arithmetic operations we expect it to do. Your question?
Where does the trend signal?
From the mechanical part.
Doesn't show.
Hmm?
The slides doesn't show.
Slides don't show the mechanical part, so what's happening is serve and change is going to some mechanical part and done is coming from the mechanical part. So this is, think of it like this. Something mechanical and this done is coming from it. Okay. So I give the mechanical part a pulse saying release a can. When it's done, it returns. And I tell it release a nickel. When it's done, it comes back. And it's the same done thing.
So 1, 2, and 5 stand for.
So basically, remember, you have a nickel, dime, and quarter. So 1 stands for a nickel, 2 stands for a dime, 5 stands for a quarter. Okay, so this register where I'm accumulating how much money I have, how much money I owe to the user, is the data state. It's the state of the data. Okay, so in operation, how would it look like? It's unfortunately very, very busy slide, but just to kind of give you a sense of operationally what would happen or what should happen in something like this is, so when you start out, there's a reset. The whole machine is reset. Then the user starts depositing coins. So see this pulse out here, this basically says nickel deposited. Likewise, there's a dime deposited here. Later on, then at this stage, the dispense button is pressed, but we do not have enough money, so nothing is dispensed. Then a quarter is deposited here. This time around, the button is pressed, and we have enough money, so the serve button is service come out. Okay, the serve signal goes out here. See this guy, and as a result of serve being done, done will go high and then done will go low. So you have to wait for done to go high and then the done to go back to low. So that's what our state machine does. it first waits for done to become high and then done to go low. And at this stage, it checks does it have money to return. In this case, it turns out there is money to return. So now it does it returns a change. So there is a nickel returned here and a nickel returned here. And then once the money is down to 0, you will see this done signal again, and then we come out of it. So the sequence of steps which is happening, and of course every time depending upon how much money the user deposited and all, the precise timing diagram was different. That's what kind of at the highest level you would like the machine to be able to do. And I was pushing there.
Like on the previous slide, can you explain what cell val, cell add, n, and cell next?
This one?
Yeah.
Okay.
Before like one's related with the mux.
Oh, you're talking about these?
Yeah.
Okay. So these are basically commands which are coming from the state machine, which are going to be selecting which of for the three various multiplexers, which one to select. Okay. So your logic of remember we have not yet designed the controller completely, right? So what would happen is whenever I want to, let's say, whenever the user deposited a money, okay, so what will happen? Let's say the user deposited a quarter. Okay, so what we'll do is cell val will be set to 0 so that 5 comes in. This one would be set to so that the lower value comes in. Okay, because I'm trying to add the thing as a remember this one, the upper one, this input is when I'm holding value. I take it back. I have to add. So this one will be set to 1, subtract or add. So it says sub add n. So if it is 1, it's a subtraction. If it is add, it is a 0. So what will happen is we'll put a 0 out here. I will select this guy. So I'll put a 0, 0, 0. Sorry. I'll put a 1, 0. Sorry. It would be 0, 0, 0, 1. So I'm depositing a quarter. So quarter deposited means I need to select this one. So I will say 0, 0, 0, 1. I have to do an addition. So I'm going to put a 0 here. And then finally, I have to take this input, which is input number 1. So it would be 0, 1, 0. And the effect of that would be that the data path would add 5 nickels to the counter. My counter is maintaining not the money, but the number of nickels, number of equivalent nickels. Oh, this register.
So does that mean like usually like your top mux one is usually like the one if like nothing is added but it's like waiting? Is that what's used for?
Okay, so this mux. Sorry. This mux is used when I'm just holding value. Okay. This one is not a mux, it's an adder subtractor. So I can either add or subtract depending upon what is happening. If I am dispensing, then every time I'm dispensing, every time the nickel has been released, I'm going to subtract out here. In which case I'll be subtracting 1 nickel. So I'm going to select out here. When depositing is happening, it could be a nickel or a dime or a quarter. So depending upon what type of coin it is, I'm going to select the first mux, and then I'm going to do a addition out here. Okay, so that's the operation.
Why do you connect the price to the first mux?
Why do I connect the price to the first mux? So let me see. Would we be using it? Yeah, to subtract the money away. So every time I have dispensed a coin, I'm going to subtract the amount of the price from the money. So that I have the amount of money remaining, and then I will dispense nickels corresponding to that. Right? Change. So basically, every time once the can is dispensed, I want to subtract the price away to get the remaining money, the money I owe, and then from that I'm going to keep subtracting nickels until I hit 0. Now again, I would emphasize, look, there is no one right way of doing it. Okay, so this algorithm out here is that we are maintaining a variable called amount of nickels, number of equivalent nickels I have. Okay, and every time a coin is deposited, I increment it. So if it's a quarter, I increment it by 5. If it's a dime, increment by 2. If it is nickel, by 1. Whenever I dispense a coin, I subtract price from this variable, and then when I'm returning the change, every time I dispense a nickel, I subtract 1 from it until I return zero. Okay. So essentially, this intuitively kind of corresponds to how you might do software, and all the operations you might do in software, arithmetic operations, are not lumped into that.
Why is 125?
Huh? 1 to 5, nickel, dime, quarter. A quarter is 5 nickels. Okay, and the price is in terms of number of nickels. Okay, any questions on this one? This is a complex example, so I would strongly recommend reading that section of the book, as well as perhaps necessary. Let's look at the lecture notes again. There's a lot going on out here because first time you're seeing Datapath and control come together. During the discussion section, the TAs will go over some examples. We have identified some, so you'll see some additional examples. But just make sure to spend time on this. So going to the timing diagram, the nickel deposit is happening there. The deposit dime, So nickel deposit, dime deposit, an attempt made at dispense, but it fails because there is not enough money there. 2 quarters are deposited. Then another attempt made at dispense. This one succeeds, so the drink is served. The first nickel is returned. The second nickel is returned, and we are back to square one. Okay, so we're moving to the next example. Okay, so that was a vending machine, a simple one, and kind of again, main thing you should always do is kind of see whether there's stuff you can do into the data path so as to keep your life simple. And the idea is that you think on what my data path should look like, and that would be driven by what kind of operations you need to do. In this case, the operations were kind of obvious. I had to keep track of money. Coins are being deposited, coins are being dispensed, the drink is being dispensed. So you have to do some additions, some subtractions, and so on. Okay.
Is the enough and the zero, is that considered feedback control?
Which one?
The thing you got from,
You're talking about this?
yeah.
It's a comparator, and whose output is 1 bit, and it's going back to the controller.
So is that considered?
That's a status. That's the status for the data path.
So it's not feedback control, right?
Well, this whole thing is feedback control. I mean, we have, I guess, I've not used the term feedback control here at all, but there is obviously feedback out here. Data path gives commands, controller gives commands to data path returns status back. So there's feedback. It's not necessarily feedback control as you study in 141. Okay, so let's look at another example, and it's a combinational log. So the project obviously is similar in flavor. So what I have is a decimal keypad. This keypad is different from the one which I have given in the design assignment. So this keypad, again, the decimal keypad, the output of this keypad, there is a 4-bit key value which tells me which key it is. So with 4 bits, I can represent all the 10 possible decimal keys, and I have a key valid. So whenever a key is pressed, a valid key is pressed, the key valid is high, otherwise key valid is low. And whenever key valid is high, key tells you which key it is. Okay. This is different from the design assignment where I have a separate signal for each of the keys. Okay. User enters a sequence of digits and then presses enters. The sequence, the correct sequence is stored in some internal memory, and its length is available as a variable. Okay, so the idea is that so unlike the homework where the user code is 3 bits, three numbers. Here it could be any number of numbers, but the length is given to you as another variable. So it could say, my code is 7. So then you have to check 7. If the sequence is correct, the unlock output is asserted. So there is a there's a mechanism in the lock, and you're going to send it an unlock signal. To relock, the user presses enter again. Okay. If the sequence was incorrect, a busy output is asserted, and a timer is activated for a predefined period of time before the user can try again. So the idea is, if I punch in the wrong code, then for some period of time, the lock will lock me out, so that I cannot just keep trying codes again and again. The lock will lock me out, and I can retry only after that timer has expired. So you can think of timer as another piece of hardware, and I can start the timer, and then when the timer is done, it will send me a done signal. And meanwhile, the user, I have to ignore any input from the user. Key valid and enter are pre-processed to be valid for 1 clock cycle per press. So some other electronics has taken care of the fact that when the user presses the key, the user may press the key for multiple clock cycles. Some electronics out there make sure that for every time I press a key valid is high for exactly 1 clock cycle. Okay, so it has done that cleaning up for you. In the design homework, we are not doing that cleaning up. You have to worry about it. So here, some electronics has taken care of it. Usually, these kind of circuits are called debouncing circuits. They kind of take care of mechanical switches having to take care and all. So what you are getting in this problem is a relatively clean signal. Every time the user presses a key valid will go high for 1 clock cycle and will have the right key code along with it. So even if the user held the key, pressed the key for a long time, key valid will come only for 1 clock cycle. So now again, we are going to partition it into data path and control. So usually it is, I find it easy, and it's usually the case that you start with a high-level view of the control. What is happening in my system? So when we start out, the system intuitively is in a mode where it's waiting for user to enter the keys and enter the code. So what will happen is the user is sitting out here, and stuff is being entered, and at some stage, if there is an enter and there is no match, then let's see what's happening. Yeah, if there is an enter and there is a match, then you open by making the unlock, and then you come back to the enter state. If on the other hand there is not a match, then what you do is you start a timer, and you have to wait until the timer has expired and before you kind of go back. So what's happening out here is that if you go this downward going edge, it says valid and key does not match. So you wait, you go into this thing out there, and then you kind of wait for the timer. So we'll see the data path would have some sort of a timer, and then we kind of wait out here in a busy state, and only when the timer says done am I going to go back. So this is a very sketchy state machine, but that's what's happening. In a valid case, I open, go back out here. In an invalid case, I kind of have to go through this kind of a sequence that I have to wait for the timer to go through. So we start in the enter state. So data path is giving me a couple of status signals. One is called key match, K match and L match, and it's also getting an enter from the keypad. It stays in the enter state as long as correct digits are being pressed. So the user is pressing the keys, and as long as it is pressing the keys in the correct state, it stays put out there. It unlocks if the enter, if it is in the enter state and enter is pressed and the length matches. So the user has pressed the right number of buttons. So remember, in our case, in this lock, the length of the code itself is variable. So the data path is going to keep track of it. So the data path is keeping track of other key presses matching, and is the length right. So if there is a match, so I'm going to stay put and enter as long as correct keys are pressed, and then at some stage, if there is the length match also happens, then I go to the unlock state. If on the other hand, the length match does not happen, so the user pressed the open button, the enter button, and there is no length match, then I'm going to go into the busy mode. So it unlocks if I'm in the enter state and enter is pressed and the length matches, and the length is coming from the data path. So L match and K match are coming from the data path. If an invalid key is pressed, then we move to wait 1. And it stays there until enter is pressed, and then it moves to wait 2. So the invalid key in this case would occur because 2 keys are pressed, or one of the invalid key codes are present. We have 16 key codes, but we have only 10 keys. So if it so happens that an invalid key code is coming, then we are also going to stay put out there. And then finally, if enter is pressed, but only part of the sequence was entered, then you go into wait 2. So let's say my sequence was supposed to be length 7, and let's say it was 1, 2, 3, 4, 5, 6, 7, and I press 1, 2, 3, 4, enter. So 1, 2, 3, 4 was correct, so it was staying put into the enter state. But now when I press enter, so the length match didn't happen. So what is happening is I'm going to take this transition. So the user pressed the enter, but the length match is not there. Then I'm going to go into this wait 2 state, and I'm going to wait there until the timer expires. Whereas, so again, this open state corresponds to, so if I keep pressing the correct keys in the correct sequence, I will stay put out here. If the correct keys have been pressed in the correct sequence, and therefore there is a length match happened, so the full code is pressed, and the enter is hit, then I go to open. If on the other hand an invalid key is there is not a key match, so incorrect key is pressed, then I'm going to go out here, and then I'm going to wait in this state, and then upon hitting enter, I'm going to go out here. So for example, what may happen is my code was 1, 2, 3, 4, 5, 6, 7. What I did was I pressed 1, 2, 3, 8. So 8 is invalid. So upon pressing of 8, I'll go from here to this wait 1. And then I will wait there. The user may press other keys. So like 1, 2, 3, 4, 8, 5, 6, 7. It may keep pressing keys. At some stage, it's going to press enter. So I'll wait out here now because I know at least one incorrect key has been pressed. So I'll wait in wait 1. When the enter is done, I go into wait 2. And now I have to do the timeout. So I'm going to do that. And when the timer is done, I'm going to come out of this. And then finally, in wait 2, I have to start the timer and wait for it to be done. So in the wait 2 state, I'm going to give out some sort of a signal to start the timer, and then at some stage, the timer would return a signal to be saying it expired, I can come out of that state. So what I've done out here is I've kind of made an assumption about the data path. Data path is doing some stuff. Data path is keeping track of keys. It's keeping track of matches of keys, whether the length is matching. It has a timer. All of that I have assumed in the data path, and without still designing the data path, we kind of went ahead and designed a controller for it. And then we will kind of go back and design the data path. So there's a lot of assumptions that you'll have to make kind of intuitively that, you know, some stuff we know like matching keys, counting keys, those sort of things are best done in Datapath. We'll assume the Datapath is capable of doing it, and then as we design our controller, we kind of make some assumptions about what kind of signals are coming to us, what signals we are sending to it. So in this case, I have to send something, the Datapath is sending me K-match, L-match, and all, and I'm telling the Datapath to run the time. Push.
Does that mean that like because you have not K match already, like you know when you press enter for not K match, it's already like it goes straight to wait one. Does that mean that like you can assume that when you press enter and L match, then K also matches in a sense? Is that what you're?
Okay, so what? Okay, so what is happening on? You're referring to this downwing arrow?
Yeah, I'm referring that. I'm like comparing that one with the one that goes to open.
Okay, so in case of open, what is happening is that the enter key was pressed. So if you just go back and excuse me, there is a key called enter also. Okay, so unfortunately the enter is being used in two different ways. Let me see. Yeah. So enter, there is a state call enter, but then there is also key call enter. Okay. So what's happening is this horizontal edge is taken when the user presses enter, and at the time the user pressed enter, the data path says length match is true. Okay. So for example, let's say again, given my code was 1, 2, 3, 4, 5, 6, 7, the user pressed 1, 2, 3, 4, 5, 6, 7, 8, enter. Now what will happen is no length match will happen. Okay, length match will fail. Actually, even prior to, sorry, that's a bad example. 1, 2, 3, 4, 5, 6, 7 is the code. I enter 1, 2, 3, 4, 5, 6, enter. So no invalid key has been pressed yet, right? 1, 2, 3, 4, 5, 6 was a prefix of my true code, but the length match did not happen. Okay, so that's the case under which L match would fail. Okay, now so if so enter at the time of enter, if L match is true, length has matched, I go open. If length didn't match, I go to wait 2. And the other thing is that incorrect key was pressed. So I did 1, 2, 3, 5. The data path would detect that 5 did not match, and then it would send me a K match to be 0. And then I would go down.
Why is valid still high in that case?
Why is valid still high? So I have to see what valid is doing, but I think valid and not K match. I think.
So valid just means like it's a number.
Yeah, let's wait on a sec. Let's get on to clear what is valid. I don't recall offhand. I think it's probably referring to that as a key being pressed. I think that's probably the case because it has to be a key, actual key press. But wait on, I don't know precisely. Any other question? There's a hand being raised over here.
Why do we have to enter with one status? So if we have a wrong number, then we can just go to busy and show the.
Oh, yeah, out here? Why? Because remember, what's happening is our notion was we stay in the enter state. That also means that any key that has been pressed thus far is a valid part of the key, valid part of the code. So this state is remembering that a wrong key has been pressed.
So why not just go to the busy state?
Why? Because I still have to wait for the user to do the enter for security reasons. So this goes back to yeah. If sequence was incorrect, a busy output inserted and a timer activated before the user can try again. Okay, so the idea is that we have not let the user try. So you want to avoid this possibility that the user presses 1 and then let's say wrong. Okay, I again press, and so just in 10 attempts, I would discover the first key. Okay, so let's say my code was 1, 2, 3, 4, 5, 6, 7, 8. Okay, with the strategy you are proposing, what will happen is I'll press 2, it will say, oops, timer, 3, timer, 4, timer. Okay, so in 10 attempts I will discover the first key. Another 10 attempts I will discover the second key. You will not make for a good lock maker. So the thing is, you actually want to wait until the enter is done before you do it. Okay?
Can you just like, I'm going from enter to open, can you just add can you just do enter and L match and K match?
Let's go to the state machine.
Or can you just not have to?
Yeah, say it again now. Which one are you talking about?
Going from enter to open, can you just have enter and L match and K match?
Enter and L match and K match. I guess the thing is, if there wasn't a K match, you wouldn't have received an L match also. Right? So it would work, but it would be different.
So why do we have to enter again after the open state?
Oh, to go back to lock state. Remember, the locking strategy is that you have to press. Okay. While I'm in the enter state, the door is locked. Okay. So this is kind of this high level of the state machine. But like I said, what happened at this stage is, as we are going through the state machine part, I'm making assumptions about the data path. So I'm kind of designing the data path, but we haven't kind of shown you the data path. So let's kind of do that. So my data path has to.
Why shall we compare the length? So we can implement differently, just compare the two codes if they are equal.
No, the thing is, in this case, the code is variable.
Yeah, but we can still compare the memory with the inputs.
Oh, the thing is, you don't know how many elements in the memory you go through. The memory itself, my memory may be 128 bytes long. My code may be only 7 bytes. Okay, so there are two ways you can do it. You can say I have a special character in the memory which indicates the end of the code, or I can give you the length of the code. So we made assumptions along the way around the data path. So let's see what the data path would look like. So data path is going to be receiving the key, 4-bit key. It is getting a reset signal. It is going to get from the controller signals called increments and load. I have a timer. When the timer fires, it gives me a done. I have length of the code as available to me from the outside world, so that's sort of programmed in. Every time a key is pressed, I am going to do this increment of the counter, how many keys have been pressed. So I have a L match coming out of this equality comparison, and every time a new key is pressed, this index goes up. So whenever we start out, index is 0. So I'm looking at the first entry of my memory. Then a key is pressed, index goes to 1, and so on and so forth. So I'm walking down this ROM. So output out here is the current value of the code. And I'm going to compare this thing against the key. And then use that against K-match. This actually, you could imagine if you are attempting the optional part of the design assignment, it has a little bit of a property like this, because there also, while the length of the key is fixed, the code itself is programmable. So that's a twist in the design assignment. So you could imagine, instead of using a ROM, you can use a bunch of registers. One register stores the first entry of the code, another register holds the second entry of the code, and so on and so forth. And then as you are walking down from one register to another. So you could kind of use the same idea there if you are attempting the option part. So looking at this, what's happening is, in the ROM is stored my code. Length coming from outside world tells me how long the code is. As the user keeps pressing the keys, I keep incrementing the counter. And so that whenever a key comes, I am comparing it against whatever it needs to be compared against. So K match tells me whether the current pressed key matched the corresponding key in the stored in the code. L match tells me that has the user pressed the requisite number of keys. So when I start out in my example of 1, 2, 3, 4, 5, 6, 7, when I start out, I'm looking at the first key. But L match would not be a match because I have only pressed one key. So the condition that has to hold true eventually is that K match has to be true and L match has to be true. And if along the way K match is not true, then in our state machine we immediately went into this wait one state. So we kind of moved out of. So enter means that door is locked. The user has pressed some number of keys. They are all correct, but he has not pressed all the keys. That's basically being an enter means. If the user presses a wrong key, we move to wait one. We move to open if the user has pressed correct keys and the right number of keys. And we move to wait two if the user has pressed correct keys thus far, but not all of them. Okay, so those are the three situations that we have, and our data path supports them all those operations. And then finally we have this timer. The timer has to wait for a certain time, so there is this t wait, which is some constant, and this load is going to be done by the state machine. The state machine is going to load the timer and then let it run. So this part of the data path, it compares the length, compares the value of the key which was being pressed, and the bottom part of the data path is implementing the timeout that we need. So these are both parts of the data path. Okay, and I have not kind of fleshed things out for you fully, but sort of you'll have to figure out from the state machine how do you control the data path.
Wait, did you just say that like the wait period is used like in the timer area? Because then like
Hmm? Okay, so the load will come from the state machine, and it will tell the timer to, it will load a value into the timer, a constant, whatever, how much time. So let's say I wanted to count down for 10 seconds. Huh? That would be T word. Okay, so let's say my counter was running on a 1 megahertz clock. Okay, and I want to count down 10 seconds. Then I will have to load a value of 10 million into my counter. Okay, and then the counter will count down until it is 0. So the value you load into the counter depends upon how fast your counter is. One exercise I would encourage you guys to do is in Logicsim, you have a timer. You can feed a clock to it. You can set. You can load the counter with a particular value, and you could actually see it counting it down in real time. How many of you have tried Logicsim running a clock in it? Anyone? No? One? Let me do it for you online. Okay, so do we have time? A few minutes. Okay, let's. Okay, but before I do it, so in summary, data path is state machines written in a particular way. Complicated problems, you have to kind of split them in these two ways. So let me take this time to kind of do the bit of a Logicsim for you guys. Okay, so let's pick up a counter. Let's make this this counter is 8-bit. Let's make it 10 bits. Okay. Let's get a clock. And let's hook up the clock this way. And let's see. Let's take a wiring splitter. This takes 10 bits in, and it has a fan out of 1. And I'm interested in only okay, so what I've done is I've created a counter of 10 bits. I'm clocking it with a clock. I have a wiring splitter with which I have just extracted the MSB. Okay, and as the count, and this is a counter which will wrap around, so it'll keep counting. Okay, and what will happen to MSB? MSB would be 1 half the time, it would be 0 half the time, right? So it will go all zeros through whatever 0 followed by all ones, and it will roll over to 1 followed by all zeros, and then so MSB will remain high for half the time. I have 10 bits. 10 bits is how much? 1000, right? So actually, let me. So if I so 10 bits is 1000. So if I control it by 1 kilohertz clock, then half a second it would be high, half a second the 10th bit would be low. Agreed? Right? It's a 10-bit counter. I'm looking at the MSB. If I'm setting the clock to be 1 kilohertz, then 1 kilohertz, 10 bit is 1000. So after every second or so, it will wrap around. I would set it to half. Okay, let me hook up an LED. So let's go to I/O. Let's get an LED. We hook up the LED out here. Let's make the LED on color to be red. Okay, good. Okay, then the other thing I do is I go to the simulate menu. I go to tick frequency, and I set the tick frequency to be 1 kilohertz. Okay, and now I'm going to let it run. And if I haven't messed up, things should work. See how the LED is blinking? I don't know if you can. Went red, went black. Kind of perhaps a bit hard to see on the projector, but red, black, red, black. Okay, so what I'm showing you is that how you can use Logisim as kind of a real-time system. Okay, so as a clock, you can set the clock frequency. Clock frequency can be at most 4 kilohertz, and then I'm running it, and you can kind of see actually that's what it's doing. Right now, how accurate is 1 second is probably not very accurate. This is not a real-time system, but you do see that as the behavior is kind of as expected. So you don't have to twiddle the clocks by hand. In Logisim, you can let the clock run at a frequency that you can set. And we can change the frequency. So the way to do this thing is you first stop. So tick disable, go to frequency. Let's say I change it to 512 hertz. So it should slow down. I reset the simulation and I tick enable. So now you can see the duty cycles, it slowed down the whole time. So when you do the log examples for the design assignments, use this clock. You should set your clock to be something reasonably high, and then you can kind of press buttons and stuff like that as if you would on a natural clock. Okay, so I'm going to stop out here, and again, discussion section, the TA will go over some more examples.